Welcome to the St. Joseph College for Women, Autonomous Visakhapatnam. Department of Mathematics welcome you for the online course on Real Analysis Module 4 Infinite Series. Myself G. Yosna, Assistant Professor, Department of Mathematics, St. Joseph College for Women, Autonomous Visakhapatnam. In the last module, we discussed so many tests, that is root test, ratio test, Rabbit's test. In this module, we discussed alternative series and based on the Leibniz test. What is alternative series? A series whose terms are alternatively positive and negative is called an alternative series. An alternative series may be written as u1 minus u2 plus u3 minus u4 plus so on plus minus 1 whole power of n minus 1 into un plus so on, where un greater than 0. Example 1 minus 1 by 2 plus 1 by 3 minus 1 by 4 plus so on. It can be written as sigma n equal to 1 to infinity minus 1 whole power of n minus 1 into 1 by n. So in this example we have alternatively using positive as well as negative. Therefore this type of series is called the alternative series. Now coming to the theorem. Our next theorem is Leibniz test. What is the statement? If sigma un is a sequence of positive terms such that we have two cases. First one, u1 greater than or equal to u2 greater than or equal to u3 greater than or equal to so on greater than or equal to un greater than or equal to u of n plus 1 and so on. And second one, limit un equal to 0, then the alternative series sigma n equal to 1 to infinity minus 1 whole power of n minus 1 into un is convergent. That is, we have to show that in this theorem. Now coming to the proof. Given that sigma un is a sequence of positive terms such that already in the statement we can take that one u1 greater than or equal to u2 greater than or equal to u3 so on un greater than or equal to u of n plus 1 and so on. And second one is limit un equal to 0. In this theorem we have to prove that the alternative series, that is sigma n equal to 1 to infinity minus 1 whole power of n minus 1 into un is convergent.
We prove that alternative series is convergent. For that we take the alternative series. Let Sn equal to u1 minus u2 plus u3 minus u4 plus so on plus minus 1 whole power of n minus 1 un be the nth partial sum of sigma n equal to 1 to infinity minus 1 whole power of n minus 1 into un. Now we take S of 2n, that is equal to u1 minus u2 plus u3 minus u4 plus so on plus u of 2n minus 1 minus u of 2n. The same way we can take S of 2n minus 2n plus 2, that is equal to u1 minus u2 plus u3 minus u4 plus so on plus u of 2n minus 1 minus u of 2n plus u of 2n plus 1 minus u of 2n plus 2, that is equal to from u1 to u1 to minus u to n, we know already, we can see in the above, that is S of 2n, write down here, plus u of 2n plus 1 minus u of 2n plus 2. Fine. After that S of 2n is subtracted from the S of 2n plus 2. We can subtracting, finally we get u of 2n plus 1 minus u of 2n plus 2, that is greater than or equal to 0. By the node point 1, that value is always greater than or equal to 0. Based on that we can get S of 2n plus 2 greater than or equal to S of 2n. So therefore what you observe, it is nothing but the increasing sequence. Therefore sequence S of 2n is an increasing sequence. And also we should calculate S of 2n is equal to, already we know that S of 2n is equal to u1 minus u2 plus u3 minus u1 plus so on plus u of 2n minus 1 minus u of 2n. That can be written as u1 minus taking common u2 minus u3, again minus common u4 minus u5 minus so on minus u of 2n. Therefore it is nothing but the u1 minus remaining we should write on the one term, that is u2 minus u3 plus u4 minus u5 plus so on plus u of 2. This value is always less than our u1. So by the condition of the bounded above, it satisfies the condition. Therefore sequence S of 2n is a bounded above. So finally what you observe here, sequence S of 2n is a increasing and bounded above. Increasing and bounded above by the known theorem. Therefore our sequence S of 2n is convergent. Once it is convergent, it is existing the limit. So therefore S of 2n is convergent to L, that is limit S of 2n equal to, we can take L. Next one we can take subsequence S of 2n minus 1. It can be written as S of 2n plus U of 2n. That implies both sides we should apply the limit. Limit S of 2n minus 1 is equal to limit of S of 2n plus U of 2n. That is equal to limit S of 2n plus limit of U of 2n. That is equal to limit of Sn, already seen the above, that is equal to L, and limit of U of 2n. From the statement of the second condition, value becomes 0. Therefore L plus 0, that is nothing but L. So what you observe here, subsequence is also convergent to L. So since sequence S of 2n, sequence S of 2n minus 1 are convergent to L, so both S of 2n and S of 2n minus 1 are convergent. Therefore the main sequence Sn is also convergent to L. So sequence Sn is nothing but what is that? It is a series of the alternative series. Therefore sigma n equal to 1 to infinity minus 1 whole power of n minus 1 into un is a convergent. So now coming to the problems. Based on the alternative series, we can start the problem. That is the first problem. Prove that 1 minus 1 by 2 plus 1 by 3 minus 1 by 5 plus so on convergent. So now we want to show that here alternative series is convergent. Alternative series is convergent mean how we prove that? By using the Leibniz test. What is our Leibniz test? Alternative series, it can satisfy the two conditions. First one is increasing and limit un equals 0. Therefore alternative series is convergent. Based on that, first we can take alternative series. 1 minus 1 by 2 plus 1 by 3 minus 1 by 4 plus so on. It can be written as sigma n equal to 1 to infinity minus 1 whole power of n minus 1 into 1 by n. So here un is equal to 1 by n. Clearly we know that un is greater than 0 and un greater than u of n plus 1 for all n. So and immediately we should calculate the limit un. Limit of 1 by n, what is that? It is 0. It satisfies the increasing condition and limit un equal to 0 by the alternative series. By the Leibniz test, the given alternative series is convergent. Hence prove that given problem. In the same way we should prove that the second problem. What is the second problem? Examining the character of the series. Sigma n equal to 1 to infinity minus 1 whole power of n minus 1 into n by 2n minus 1. So here we know that un, what is our un value? N by 2n minus 1. Now we should calculate here un minus u of n plus 1. That is equal to un, we know that n by 2n minus 1 minus u of n plus 1. Instead of n we should add on the n plus 1. So that's why n plus 1 by 2n plus 1 after simplifying. Then simplifying, our LCM is 2n minus 1 into 2n plus 1, and numerator we will get n into 2n plus 1 minus n plus 1 into 2n minus 1. Finally simplifying, 2n square plus n minus 2n square plus n minus 2n plus 1 by 2n minus 1 into 2n plus 2. Finally we can simplify. Finally we will get 1 by 2n minus 1 into 2n plus 1. That is greater than 0. So increasing sequence condition is satisfied. Now coming to the second condition. What is the limit un? So that is equal to limit of, what is the un value girls? N by 2n minus 1 in the numerator n, in the denominator n taking common 2 minus 1 by n, that is equal to n get cancelled, 1 by 2 minus limit of 1 by n value 0. Finally we will get 1 by 2. So it is equal to 0 or not equal to 0? It is not equal to 0. So limit of un not equal to 0. Here our second condition is failed. So second condition is failed by the Leibniz test. The alternative series is, what is that? It is convergent. Therefore here we are existing the not a convergent. Now next problem. Prove that sigma n equal to 1 to infinity minus 1 whole power of n by n factorial. It can be written as 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial plus so on. We prove that it is convergent. So first we take un. What is our un value? 1 by n factorial. Clearly un is always greater than 0 and un greater than u of n plus 1 means it is nothing but the our series satisfy the increasing condition, that is nothing but in the Leibniz test first condition is hold. Next we should calculate the limit un what is that? 1 by n factorial. As a limit of 1 by n, what is it? It is 0. Second condition is also hold. So by the Leibniz test our series, our alternative series sigma n equal to 1 to infinity minus 1 whole power of n by n factorial is convergent. And next one, fourth problem. Examining the convergence of 1 by 1 into 2 minus 1 by 3 into 4 minus 1 by 5 into 6 so on. So now take that problem and it is also written in the alternative series condition. What is that? Sigma n equal to 1 to infinity minus 1 whole power of n minus 1 by 2n minus 1 into 2n. We should add an nth term of this alternative series. So clearly we observe un equal to 1 by 2n minus 1 into 2n. Clearly our un is greater than 0 and also it holds the first condition. What is that? As increase in sequence of the Leibniz test, it is also hold. And also second condition, limit of un. What is our un? 1 by 2n minus 1 into 2n, and it's nothing but look like a limit of 1 by n. So limit of 1 by n is 0. So in this problem the Leibniz test of the two condition is hold, increase in sequence and limit of un is 0. So two condition is hold. By the Leibniz test our series sigma n equal to 1 to infinity minus 1 whole power of n minus 1 by 2n minus 1 into 2n is convergent. Next definition, absolute convergent. The series sigma un is said to be absolutely convergent if sigma mod un is convergent. So the given series is absolutely convergent mean its modulus is satisfied the convergent definition. Then it is called as a absolute convergence. Next coming to the conditional convergent. What is the conditional convergent? If sigma un convergence and sigma mod un is divergent, then we say that sigma un convergence conditionally. Then it is called as a conditional convergent. So sigma un convergent and its modulus divergent, then we say that the sigma un convergence conditionally. Now coming to the based on the theorem. What is the theorem? If sigma un convergence absolutely, then sigma un convergence, or an absolutely convergent series is always convergent. What is its meaning? Absolute modulus of un is convergent, then sigma un is convergent. That is proved that in this theorem. So for that proof, let sigma un convergence absolutely. Convergence absolutely mean what is that? If modulus convergent. What if we prove that in this theorem sigma un convergence? So since sigma mod un convergence, that implies by the known theorem, by the quasi-general principle of convergence for series given epsilon greater than 0, there exists m belongs to n such that modulus of mod u of p plus 1 plus mod u of p plus 2 plus so on mod q uq less than epsilon for all q greater than or equal to p greater than or equal to n. Already seen the module first module. Based on that, mod of u of p plus 1 plus mod of u of p plus 2 plus so on mod of uq is less than epsilon. Therefore modulus of u of p plus 1 plus u of p plus 2 plus so on plus uq is can be written as less than or equal to mod of u of p plus 1 plus mod of u of p plus 2 plus mod of u of q. This value what is that? Less than epsilon. So therefore modulus of u of p plus 1 plus u of p plus 2 so on uq is less than epsilon. By the quasi general principle of convergence, our series sigma un convergence. Now note point. What is our note point? The convergence of the above theorem is not true. What is that? That is sigma un convergent, but its sigma un is not absolutely convergent. It means the series convergent, but its modulus is convergent or not, we don't know everything. So sigma un convergent, but its modulus is maybe convergent or divergent. So that is example sigma minus 1 whole power of n minus 1 by n. It is maybe convergent or divergent. So we don't know clearly. Next, based on the absolute convergence, we can solve one problem. What is the absolute convergence? Sigma un is convergent, then its modulus is also convergent. Then it is called as the absolute convergence. Now that is seen in the one problem. What is that? Show that the series 1 minus 1 by 2 plus 1 by 2 square minus 1 by 2 cube is absolutely convergent. So for that, first take the given series. Given that 1 minus 1 by 2 plus 1 by 2 square minus 1 by 2 cube, so on. It can be written as sigma minus 1 whole power of n minus 1 into 1 by 2 power of n minus 1. So let sigma un is equal to sigma minus 1 whole power of n minus 1 into 1 by 2 power of n minus 1. Now we can take modulus on both sides. Sigma mod un equal to sigma mod 1 minus 1 whole power of n minus 1 into 1 by 2 power of n minus 1. We can apply the modulus. Negative can be written as positive. So therefore sigma 1 by 2 power of n minus 1. So already seen the first module by the geometric series, sigma 1 by 2 power of n is what is that? Convergent. So condition sigma r power of n is convergent if r less than 1. Based on the condition, our series is convergent. So it is nothing but which one? Modulus. Therefore sigma mod n is convergent. So sigma un is convergent, then its modulus is also convergent by the definition of absolute convergent. Therefore sigma un is absolutely convergent. Thank you everyone.